Okay, so in this problem, 237 out of the book, again we want to find the horizontal and vertical reactions at A and C. And again, it's like I mentioned before, it's hard to see, but this B connector is a pin. You can see the symbol there. And that's important because if not, I would have two reactions at A, two reactions at C, one free body, three equations of equilibrium. It's be an indeterminate problem, and we're not ready for that yet. So we're going to take this apart. So the first thing I want to do is take it apart. So I can draw a free body diagram of AB and a second free body diagram of BC. Okay? So let's do that. So I'll start with, where should I put? I think I'll do it up here. So this will be my free body diagram of, I'll call it AB. So I'll draw it. So there's AB. It is 5 meters tall. And at A, since it's a pin, I will assume I have a force AY and a force horizontally AX. Those are my assumptions. Now I go up here and I got to think about B. So B is a pin. Normally I'd have two forces at that point that would be equal and opposite on this force. But take a look at what's unique about BC. What's the first thing you notice? There's no applied forces on BC. Right? So BC is a two-force member. No? You don't see that? See? Pin at B, pin at C. No forces applied. External forces. So it's a two-force member. So if I actually drew a line between B and C, I know that two-force member lies along this line of action. And all I don't know is the magnitude, just like our previous problem. So that means I'm going to come up here and assume a force that I'll call the force from B to C. How many unknowns on that free body? 3. 3 equations, 3 unknowns. I should be able to solve for all those. What is that direction? Well, it looks like it goes 4 and it goes up 5, right? Did I do that right? So if you look at a little triangle to tell you the slope, it's going to go over 4 and up 5. That's not a nice triangle. It's not like a 4 or 5 something triangle. I don't know what that is off the top of my head. But that means I can break that down into a y component and a x component. So let's solve for these guys. How do I do that? Where's a good place to sum moments? A. I like that. So let's do it. So again, using... Oh, thank you. Yeah, I left off something pretty important. The load. So the load here is rectangular. The height of it, or the base of the load, is 5, and the height is 350. So 5 times 350 is 1750. Yeah. And that will happen right in the middle. That's 1750 newtons per meter, so that would be 1.75 kilonewtons. Let's do that. And it's half the distance, so from the base that would be 2.5 meters. Thank you. Yeah, I wouldn't have got too far without that. So again, we're going to sum moments about A, and we're going to assume right-hand rule, and we're going to assume everything is in equilibrium. So about A, the applied force creates what kind of moment about A? Positive or negative with my sign convention? Negative. So it has a force of 1.75 kilonewtons times a moment arm of 2.5. Now up here at B, I've got a vertical component and a horizontal component. The vertical component passes through A, does not create moment, but the horizontal component does. So I need to find the horizontal component of B and then multiply it by this moment arm, which is 5. The way I've assumed this direction here, the horizontal component is to the right, so what kind of moment does that create about A? Positive or negative? Negative. So I'll start here with negative. What is the horizontal component? Well, I mean, you can do an arc cosine and find an angle and do all that. What I like to do, and I'll draw it over here on the side so you can see it. Is if I know this is 4 and I know this is 5, I can calculate the hypotenuse of that angle. It would be 16 squared plus 25 squared. 5 squared. That's 25 plus 16. That's 40 what? 41? So I know that this is the square root of 41. So the horizontal component would be 4 over the hypotenuse of 4 over the square root of 41. A lot of our problems, these triangles are going to be really convenient, like 3, 4, 5 triangles. So it'll be 3/5 or 4/5. And there's even another one. There's like a 5, 12, 13 triangle that pops up a lot. So sometimes this approach can be a little more efficient than doing an arc sine and then going back and taking the sine or cosine angle. So that's the way I'm going to do it. So in this case, I'm going to write my component as 4 to the square root of 41. That will give me the x component of BC and times a moment arm of 5 meters. So I should be able to solve for the force in BC. So what's that? That's a little more complicated calculation.
I got 1.4.
1.4? Anybody else get that? Working on it? No?
I got 7.5.
You got what?
7.5.
That doesn't sound right.
I got 1.4. I got 1.4.
You got 1.4? Anybody else get 1.4? Miss Isabel, I see you working away. How about you, Mr. Conley? Did you get it?
Not yet.
Not yet? I like 1.4 more than 7. I'll tell you that. I think it should be less.
Yeah, 1.4.
1.4? Okay, I like that. So we'll say 1.4, and that'll be kilonewtons. And it's negative. What does that mean? It's just the opposite direction. And that kind of makes sense, too. With this big force pushing horizontally, you would expect this force to push back. I just didn't draw it that way. That's okay. So now that I know that, I can go ahead and get my x and y components at A. So I'm going to sum forces in the y direction, assume up is positive. So I've got AY acting up. No applied force, and my y component of BC is down. So I'll say minus, and the y component is vertical, so that's 5. So that'd be 5 over the square root of 41 down of BC. So just plug in your value for BC here. Negative, negative cancels. It looks like AY is also going to be negative. I don't know what that's going to be. Something less than 1.4. Maybe half of that? I'm just guessing. What's 1.4 times 5 divided by the square root of 41? Anybody else get 1.09? 1.09. I like that. We're going to have to do it one more time because if we sum forces in the x direction, 0, I've got ax to the left, so that's minus ax. And then I got the x component of BC is positive. What is the x component of BC? We've already done that before, so that's 4 over the square root of 41 times FBC. And again, we can put FBC in there, and we should find that AX is going to be it's going to be negative again. What's that value? It's going to be pretty close to this one, isn't it? Maybe a little bit smaller. So what's 1.4 times 4 divided by the square root of 41? 0.99, I'm guessing.
I have 0.875.
0.875. Anybody else get 0.875? Yep. Excellent. You'll notice that I got every one of them in the wrong direction. Do I care? No. I just made assumptions. My equations tell me where they're actually going to make it work. Now, we're not finished. Well, we're out of time for class today, but we're not finished because I need to find the reactions at C. But that would be pretty easy because I can draw a free body of C. Right? And I can assume that at CY, or at C, I have a Y, and I have an X. And what's the only force there? If I assumed FBC was down here, what's it going to be on the other side? Up. So all I have to do is take my value for BC, plug it in there, figure out my X and Y components. Because we'll find out that the X component, the Y component is going to be CY, and then there's going to be an X component which will balance CX. And we found those already. We found those as we did the previous calculation. So what I'll do is I'll go back to my office. I'll actually finish the calculation so you'll see it on the printout if you want to compare your results. All right.